We have here another problem from chapter number 5, but this time we're going to use a tilted axis because we're interested in the acceleration along the incline. And this is a trick that we use when we're interested in acceleration that's along this direction. And so we tilt our axes, so we set up our axis sort of like this in the x and y direction so that we have acceleration only along one axis. So we have acceleration in x direction is not equal to 0. In fact, we want it to be 2.0 meters per second squared. But in the y direction, because it started at rest, it's not going up or down off the incline, that's 0. And that just makes everything easier. If you can set up your axis to a line so that the acceleration is 0 in one of the two directions, it turns out to be worth it, even though there's some trig we have to do along the way. And the trig we have to do along the way has to do with finding the weight. So here's my weight force. My normal force is not pointing opposite this. Remember, normal is parallel to the surface, so the normal force is going to be perpendicular to the surface. So it's got to be set up like that. And then we have this other force, which is what our unknown is. So this right here is our unknown that we're trying to find. And so we're going to set this up and find the components again, just like we've done before. We want to say, what are the forces in the x direction to give us the acceleration in the x direction that we want? And we may also need to find the forces in the y direction to give us 0 acceleration. We may. We'll just see. So as we look at this, the trick here is to find, hey, the weight has a component that falls along the y-axis and the x-axis. Like this. So this is the mg along the y-axis, if you like, and mg along the x-axis, those components. And I realize it's a tilted axis. So I'm going to sort of untilt it for us for a minute, which may or may not help you. I don't know. You can decide which is more helpful. But if I set it up like this, then this mg is going to point this way, and I'm going to have the mgx pointing down that way, pointing backwards along the x-axis in the negative direction, and mgy pointing down. And then to figure out whether we're looking at sines or cosines, we have to figure out what one of these angles here, either this one or this one, what one of those is. So let's see if we can figure that out. As we look at this geometry, so I'm going to go back up here to this triangle. I've got 30 degrees here. This is a right triangle like this, which makes this angle 60 degrees, okay, because that's a 180 degrees total in our triangle. So that makes this also 60 degrees, right? This is 60 degrees. And so finally, that makes this 30 degrees. And this is typically the one we use, but you can certainly use this angle in here, the 60 degrees. But most people write this one as the same angle as the incline, theta. So theta in this case is equal to 30 degrees, so that's theta. And then we just use our SOHCAHTOA as usual to say that cosine of theta is equal to mg in the y direction over mg. So that's going to give me the y component. And sine of theta is equal to mgx over mg. And so what I get, of course, is mg in the y direction is equal to whatever mg is, cosine of theta. Or you could write this as force gravity y is equal to mg cosine theta, and force gravity in x is equal to mg sine of theta. This is a useful thing to sort of draw out and put on your equation sheet if you want, so you can have it as a handy reference. But I do want you to be able to set these things up because the angles aren't always set up in the same way. Okay, so we're going to use this to say, well, that's one force in the x direction. The other force that's in the x direction is, of course, this unknown force that we're trying to find. So this force of push. And then we also have the normal force, but notice the normal force just goes up. Force normal. So in the x direction, it looks like we have force of push going to the right, and then minus mg, the x component, must be equal to max. And in the y direction, we just have force normal is up minus mg in the y direction is equal to 0. So in this case, we can find out pretty quickly the normal force is just equal to mg, if I look down here at the bottom of my screen, mg cosine theta. So my normal force is actually less than, sorry, I have to scroll here, is less than my my weight, because it's my weight times cosine theta, and theta is less than 1. Okay, and then my push, which is what we wanted to find, right? That's what we wanted to find, is equal to max plus mgx. Watch your signs here. We've already put in the sign, the direction associated with gravity, so you don't have to then put another negative sign in. And so your force of push here is just mass times acceleration plus mg, looking all the way down here using this, times sine of theta. So that's what our expression looks like after we've used our SOHCAHTOA. And so now we just have to plug numbers in. So we've got force of push is equal to, the mass is 100 kilograms. This is a big cart, a big box. Kilograms times 2 meters per second squared plus 100 kilograms times a positive. When you see G in the book and in my notes, it's always going to be positive. I will have taken care of the sign, times sine of 30 degrees. And then we just plug this in. This gives us a 200. This gives us a 98 times sine of 30, which would be 1/2. So that would give us, 980 times a 1/2, 490. So this gives us a pushing force that's pretty substantial. It's right at 690 newtons. And that's what the problem asked for. If you wanted to find the normal force, you could go ahead and plug these numbers in and get the value for the normal force. But we don't need it for this problem, so you don't need to do the work. The trick to this problem, if there's a trick, is really tilting your axes, right? And the reason for doing that is so that we get acceleration in one direction is 2, and in the other direction is 0. That's the way we set this up so that we can solve it.